next up we are going to discuss acid catalyzed reactions. Over here we are going to use ammonia and derivatives that include hydroxylamine, phenylhydrazine and hydrazine. Hydroxylamine looks like this, phenylhydrazine looks like this, and hydrazine looks like this. So why do we use these is because these are weak nucleophiles. Why do we need weak nucleophiles is because we are going to attack a proton, which is H plus, in the first step. So the first step is going to be as follows. We are going to use a ketone. The lone pair will shift over here, the pi bond will shift over here, and then the positive charge will occur here. Now an H plus is going to be added to the O minus, and then an OH will be formed, and a carbocation intermediate tetrahedral carbo. Actually, this is a carbocation intermediate will be formed. Now this will attach itself to the nucleophile, and then it will form. The nucleophile would be anything like, so a nucleophile will be added, which is what we discussed. It's going to be NH2 with a Z. That could change. Either it would be hydroxyl or phenyl or hydrazine. It could be anything. Now what it's going to do is it's going to attach to the carbon like so. Now what's going to happen is this hydrogen will remove and give off itself as a proton. Now this hydrogen will also make bonds with this hydroxyl group, and this hydroxyl group will leave, this hydrogen will leave, and the pi bond will be shifted over here, and then it will form double bond Z, double bond N, Z. So this is going to be our product after the acidification. So one important thing to note is that it is a process of addition followed by elimination. And since this is a good leaving group, it leaves, and addition is addition of the nucleophile, and this is a leaving group and it leaves and it forms water at the end. So now we're going to look at the reaction with hydroxylamine. What we're going to use is acetaldehyde molecule. We're going to add the NH2 and OH. So what we'll actually do is shift this like so. This will make a bond, and then it will convert into CH3, C, bond N, bond OH, and here we have a hydrogen and here oxygen, and then it will form as acetal oxime or ethanoxide with the elimination of water.
Now the same thing happened with acetone. I used this hydroxylamine and combined the oxygen and the hydrogen here, and then the byproduct water will be formed over here, and then it will form acetone oxime or propanone oxime.
Same goes with phenylhydrazine. Here is the phenyl group, this is the hydrazine group, and now it will react with acetone. The oxygen will remove, the H2 will remove from the phenyl group. Now this will make bonds with this, and then it will form acetone phenylhydrazonia or propanone phenylhydrazone. And then we're going to start with 2,4-dinitrophenol hydrazine test, which is a test used to differentiate aldehyde and ketone, which are carbonyl compounds, from other elements, in which we use a phenyl group that has nitro group on the second position and the fourth position. Now what will happen is, let's just use acetaldehyde as an example. This hydrogen will combine with the oxygen, and then what we'll have is NH bonded with N, double bond with hydrogen, and we're going to write it like this. So the nitro compounds over here. Now what will be formed is acetaldehyde 2,4-dinitrophenol hydrazine. Now these will give yellow, orange or red precipitates. won't go into the detail what kinds will give what kind of precipitates, but we will react acetophenone as an example. Over here we have acetophenone, and it will react with the same dinitrophenol hydrazine, and it will form something like this. Double bonded to carbon, which is also bonded to the CH3 and C6H5. Now it will be called as acetophenone 2,4-dinitrophenol hydrazine. Here we have nitro groups, here we have nitro groups. Some confusion with the structure. The CH3 is actually over here. So what this means is this will remove and this will stay constant. So that's it. And then now we have the polymerization of acetaldehyde and form aldehyde in the presence of dilute H2SO4. What will happen is metaformaldehyde will be formed, which structure is as follows. There's CH2 and CH2 is combined by oxygen. This is combined by oxygen, and then there's another CH2 molecule. So this is a metaformaldehyde molecule. This is formed once formaldehyde polymerizes in the presence of dilute H2SO4. Now a structure called paraldehyde will be formed from acetaldehyde. What it means is it's the same structure, but a CH3 is added with the CH2 as so. So dilute NaOH H2SO4, sorry. So what I did was add also 3 over here. So 3 formaldehyde will combine to form metaformaldehyde, and same is the case with here. Over here 3 acetaldehyde molecules will combine to form aldehyde. Now the next is reaction of alcohol with aldehyde in the presence of hydrochloric acid. So the reaction actually results in an acetal, and this acts as a catalyst, and it must be dry gas. So what we do is we take 1 mole of acetaldehyde and react it with, let me just rearrange it. Acetaldehyde, and then we have methanol, 2 moles of methanol or ethanol, we can use whatever. So what we do is we write the CH3 over here, O over here, and H over here. So this combines with this, and then water will eliminate in the presence of dry HCl. What we'll have is, so I've written it out, is that what we'll have is this. It's a 1,1-dimethoxy-ethane, and it is also commonly known as acetaldehyde dimethyl acetate. So what will happen is that the aldehyde group may be converted into carboxylic group if it is reacted with mild oxidizing agents. So what we'll do is, to regenerate the aldehyde, we will use the 1,1-dimethoxyethane again to hydrolyze it, and then it will form the acetaldehyde molecule again with 2 methanol molecules again. So this is just so that aldehyde doesn't react with mild oxidizing agents. So the acetal is hydrolyzed in the presence of an acid back to the acetaldehyde and alcohol, which is methanol. Now something to note is that ketones do not undergo this reaction.